Hi there, my name is Alexandria Alcantara, and I am a graduate student here at UNF. I am pursuing a degree in material science and engineering, and I am also working an internship with Los Alamos National Laboratory in the theoretical division. I've been working on a project with them for the past 2 months, and this is to ensure accuracy and predictability in computational methods. So what we did is we used a very well-known transition metal thiophosphate, chromium thiophosphate. It's been studied quite extensively over the past few decades, but recently it's grown into a hot topic because it has properties of a 2D magnetic semiconductor. Now, we all might know how graphene works. It's an atomically thin layer that is strongly bonded within its plane, and so it's very useful in everyday application. However, it's highly conductive and it can't be used in everyday transistor applications. And that's why we need 2D semiconductors rather than graphene. And so because this is such a widely studied material, we want to use this as kind of a benchmark to see how accurate this new method in density functional theory is for use in predictability of its layered structure. So right now, we currently have the band gap determined, the energy band model, we have its magnetic moments, we have the ground state ordering of the magnetism. So we basically know the ins and outs of the electronic and magnetic structure of this material. And so we can model this through our computational methods, which is DFT, using a new functional in density functional theory. It's called SCAN. It stands for strongly constrained and appropriately normed. We want to test this out because it's known to have accuracy in antiferromagnetic materials specifically. Chromium thiophosphate is an A-type antiferromagnetic material, which means that it's ferromagnetic in plane and then antiferromagnetically coupled through the plane. We know that it has a magnetic moment per chromium of 2.814 magnetons, and we know the band gap is 1.4 eV. And so with these experimental values known, we can use SCAN to see how closely we can get to the actual values with our computational methods. The motivation behind this is that we currently have methods that need a push from other parameterizations. For example, PBE. It has self-interaction errors and it underestimates greatly. And because of this, there is this parameter called Hubbard U that creates a potential well for the electrons to create more magnetism in the system to overcome that self-interaction error. And we want to eliminate this extra step because it does cost time and extra computational power, and also it's still not accurate. If you look at my poster in the motivation section, you can see the experimental values compared to the PBE and the PBE+U functional. The PBE only, which is underestimated, gets the ground state ordering correct, but the band gap is too small, as is the magnetic moment. So when another study came in and added a Hubbard U to it, the band gap grew too large, and so did the magnetic moment, and then the ground state ordering was thrown off as well. So when you add a Hubbard U to the system, it completely throws off the magnetism. And so we need something that is accurate for the bulk, and also predictable for its layered structure, because we need to understand how it acts when it's exfoliated down into its layered component. And so we use Vesta to model our structure, and then we implemented it into VASP for the density functional analysis. These other parameters aren't too important, and like I said, the most important thing here is that we are using SCAN, which is a new functional. It is actually a meta-generalized gradient approximation, and we are using 8 different types of magnetic configurations to really make sure that we are getting the correct ground state considered for this study. So here I have the scan results for the bulk chromium biophosphate with the experimental values for this material. Scan not only gets the ground state order correct, but also the band gap is much closer than the PBE and the added Hubbard study, as is the magnetic moment. This is without any parameterization or optimization. So overall, with this study, we wanted to use the bulk chromium biophosphate and all its experimental values to determine how accurate scan is and use it for the predictability in its layered structure to characterize it through its electronic and magnetic properties. And so in the future, we're going to then calculate the DFT for the monolayer, bilayer, and trilayer, and make sure that our calculations are indeed showing that it is a 2D material. And then we're going to further characterize it through its optical properties for experimentalists to use in their studies. So that's basically all I have for this poster right now. Just as the bigger picture here, science does aim to reach for accurate and predictive methods, and that is what we wanted to do in this study. And so I hope that you got something from this and pass along the word about this new functional used in DFT to save time, effort, and cost with this accurate method.